about this? Oh, is that the best?
Yeah.
It's number 6. So for next week, if I forget, remember setting number 6. Can you all see well what you're writing or what you're reading in front of you? Okay, good. Let's start solving. So, because we've got a couple of problems to solve today. So, question 1. Has anybody got an answer? Adrian.
86 hours for studying, 56 for 26 for partying, and 56 for
86 for studying. How much for partying?
26.
And for education? Oh no, that's everything else.
56.
56. So what's your objective? 2p plus e. It's 112. No, 52, 108. Okay, has anybody got a better solution than 108? Because remember, here it says we were trying to make the expression 2p plus e as large as possible. So we have numbers. I trust you that they satisfy all those constraints, which I'm not checking, but is it also making 2p plus e as large as possible? Nobody knows? Yeah?
I've got 79 for studying.
79?
24 for partying.
24?
65.
65? 79, 24 and 65. So that's that. Yeah, okay. So here the objective is how much? 113? Yeah, that's better. Anybody got a better solution? Well, I've got a better solution, I think. So I've got 60 for studying, 19 and a half for partying, and 88.5 for everything else. And what I'm getting is 127.5. Aha. Can anybody do better than I can? Okay, maybe you can't, but how? But does that mean that this is the best possible? You don't know. Well, I'll show you that this is the best possible. Okay, so how do I show you that this is the best possible? Okay, I take the first constraint and multiply it by 5/4. So what I'm getting is that 5/4s plus 5/4 of p plus 5/4 of e equals, I can't remember, 210? Okay, I take the third constraint. No, I won't take the third constraint. I take the fourth constraint and I'll multiply it by -3/4. Okay, what do I get? I get that -3/4 s is less than or equal to -45. Do you agree? Okay, you don't know where I'm heading, but I'm heading towards a solution. And if I multiply this one by, what do I need to take? -1/4, what do I get? Well, -1/2 s minus 1/4 E plus 3/4 P is less than or equal to minus 75/2. I'll call these constraints I'll give them a symbol. Oh, you don't see the symbol. So this is the symbol for these three constraints. So when I add all the constraints that I've marked with this symbol, added together, what do I get? Okay, 5/4s minus 3/4 minus 2/4. So that is no s. So 0s. You see what I'm doing? 5/4s minus 3/4s minus 2/4s is 0. Okay, how many p? So what's the, so there's 5/4 plus 3/4, so that's 2p. And how much of e? 5/4 minus 1/4, so that's 4/4 of e, so that's 1e. And when I add the right-hand side, what do I get? 210 minus 45 is 165. 165 minus 37.5. It's 127.5. Aha.
Really 72.5.
117.5. Oh, I don't know. I hope not, because I've got 127.5 there. I would contradict myself. Okay, so what have we shown? We've shown that if you have numbers S, P, and E that satisfy these constraints, namely this one and the last two, then it also satisfies this inequality down here. 2p plus e is less than or equal to 127.5. Okay, so if this shows that, proves that if S, P, E satisfy all the constraints, they also satisfy that inequality here. 2p plus e is less than or equal to 127.5. Well, and that shows that my solution, this one, is optimal, because no matter what values for S, P, and E you take, you can't 5, and I've got 127.5, so there can't be anything better that you can do. Does that make any sense? Are you impressed? You should be impressed. If you're not impressed, shame on you. Okay, so sorry. No. Well, of course, no. Of course, you should ask a question now. Ask the question. Someone please ask the question. Yes?
Why do you multiply by those specific values?
Exactly, that's the question that you were supposed to ask. Yes. So why do I multiply by exactly 5/4 and 0 and 0 and minus 3/4 and minus 1/4? Okay. I multiply by these numbers because, do you really want to know? Because that's the optimal solution of the dual linear program. and you don't know what the dual linear program is. So you have to believe me that these are the best numbers that you can take to multiply the constraints with. And sometime, when do we do the dual? I think sometime in February or so, I'll show you how to get these numbers. So that's something to look forward to. Thank you for the question. Okay, any other comments, remarks, or questions about this problem?
Will the same approach work for all programming questions? Like
Yes.
multiplying multiple factors and then
Yes, but you have to know what numbers to multiply with. What you can find. Yes, we'll see. Yeah, it always works. Okay, it's a great question. It's a very fundamental question whether you can always prove that your solution is optimal once you get the optimal solution by taking some multiples of the original constraints, adding them together, and getting exactly the same right-hand side. Well, exactly the same right-hand side for the objective as you have your optimal solution. And the answer is yes, you can always do it. But that's advanced. That's second-year material to prove that it always works. Okay, good. Shall we move on to question 2? Okay. So to remind you, question 2 is, there are 3 boxes with marbles that are not transparent, so you can't see inside. But they are labeled red, green, and red and green. And the box labeled red has only red marbles in it, and the box labeled green has only green marbles in it, and the box labeled red and green has both colors in it, a mixture of red marbles and green marbles, okay? Now, if I mix up the labels in such a way that none of them is correct, you want to put the labels back in the on the correct boxes, and you want to not look inside, but you can just pull out a marble, look at its color, aha, pull out another one, aha, pull out another one, aha, and the question asks how many. What is the minimum? What is the least possible number of marbles that will make sure that you can put the labels back correctly? Is that clear? Question? What is the answer?
I didn't get an exact value, but I got sort of like I got 3 plus 2n. There's a sort of way where n is like any number after 1. Like the way I did it was like you pick out 3, 1 from each box. And the one that's different from the other 2 marbles, that box is definitely that colour because it must always be.
Okay.
And then you start drawing 2, 1 from each box, and then when the 2 marbles are different at some point, you know which colours are in the other 2 boxes.
Okay, so that can take a lot of time. Did you get the idea? Okay, that works. I'm persuaded that it works, but it's quite a lot of marbles. Can anybody do with fewer than 3 plus 2n marbles? Oh, come on, solve it now. Can anybody do with 2 marbles? Can anybody do with 3 marbles only? Yeah?
When you're taking marbles out, does it matter, does it have to be from the same box, or can you take them out of different boxes?
You can take them out from different boxes, as you wish. Are you solving? You should be solving. Okay, I'll give you a hint. One marble is enough. Now you have to finish the solution. That's it. Has everybody got the solution? Okay. I'll tell you now what it's like. So the key is, the key information is that all the labels are wrong. None of them is correct. Okay. So if you take a marble from the box which is currently labeled red and green, now if this one that you take out is red, then, well, you know that this box has to contain only red marbles because it can't be the green box because what you took out is red, not green. And it can't be the red and green box because the red and green label is wrong. Okay, so this necessarily has to be red. So that's that. Now, you look at the label on the green box, and it can't stay put where it is because all the labels are wrong. So it has to move. So the green label now has to move to this box because the third box is already labeled red. And then what you're left with is red and green here. Okay, and if the marble that you take out is green, then similarly you get a different thing. If it's green, then obviously this one's green. And this one must be red, and this one must be red and green. That's quite easy. So it has nothing to do with what we're doing in the rest, but it's a nice puzzle. So it actually does have to do because it's an optimization problem. You're trying to minimize the number of marbles that you take out. And obviously you can't do with fewer than one. Because if you don't take anything out, you don't have any information whatsoever. So there's no way you can put it back. Okay. Aha. So now you can mark your homework solutions again. There's a column for 1 mark or 2 marks, depending on how many questions you got approximately right. And And we're going to do the chess set problem. So that's the problem that accidentally was the last slide of last week's handout, but it's also on this week's handout. And that is the problem that we'll be looking at for quite some time now, because in this particular example, we'll be learning some techniques how to solve linear programming problems. Okay, I introduced what linear programming is last week, and I probably said that there are two big things that we need to learn when it comes to linear programming, and one of them is to solve the models. Once you've got the model, how do you find the optimal solution? And the second one is when you get a real-life problem, how do you get the linear programming model? They're kind of separate skills, and you have to have both if you want to be successful at solving these problems using linear programming, obviously. So let's have a look at this example problem. The problem is about a fictitious chess set maker, and they have two different sorts of chess sets, small and large. That's not it's not very inventive to call them small and large, but that's what they are. Okay, and making a chess set requires, in this example, 3 different resources, and it also requires. This wouldn't switch itself off all the time. Okay, so one resource is a lathe. Okay, that's a. Oh, I forgot to bring a picture of a lathe, but it's a machine that makes wood spin and then carves a piece out in the shape that you want. Yes, yes, except it's decremental, so you can only remove stuff. Yeah. And then the second resource that is required is wood, because you're making wooden pieces. And so the smaller set wants 1 kilo of wood, and the large set wants, what am I doing? 4 kilos of wood, but whatever. And then there's a finishing of each set. Takes some time in a finisher's workshop. Okay. So these are the 3 resources that are needed to produce a chess set. So obviously, a resource translates into a constraint because you're constrained by how much of the resource you have. We'll see that in a second. And then what this says is that the large chess sets give us some profit for every box set, every set sold, and the small one as well. And now the problem is to decide how many sets of each kind we should make. So every week. So yes, excellent. Now we know what the problem is. So the first step, if you want to solve a problem like this in operational research, is to produce a model formulation. Please, thank you. So the model, these formulations, I keep emphasizing that they always have 3 components. These components are decision variables, constraints, and an objective function. Okay, it's always the same. So you have to start with decision variables. Well, you know from the rest of your maths what variables are. They're just some letters that represent something else. So in this case, they will represent some real numbers, or numbers. Okay. And what we need, and so they are kind of unknown values, represent unknown values, things that we don't know in advance, but the optimal values of these decision variables we're trying to find. Okay, so this is what a decision variable is, and I call them x1 and x2 because I like calling them x1 and x2. But you can call them whatever you want later when you're writing your own our key models. The flashing light in the corner. I don't know what it means. Probably Big Brother is watching me. Okay, so in this case, I'll give you give it away. The decision to make is how many small sets and how many large sets we're going to make per week. Okay, so x1 is the number of small sets produced per week. And x2 can't be anything else than the number of large sets produced per week. I hope it's per week. Yes, everything is per week, so it's good to put these in weekly amounts as well. Do we know what x1 is? No. Do we know what x2 is? No. We know what x1 is, but we don't know what its value is going to be in the end. But we know that x1 is a decision variable that stands for the number of chess sets to produce every week. Okay, so once we have decision variables, we can write the objective and the constraint, and it doesn't really matter in which order, but we have to start with the decision variables, because if we don't have the decision variables, we can't write formulas possibly for any objective functions or any constraints. So let's start with the objective. So in linear programming and in many other OR techniques, the objective, it's an optimization problem that we're looking at. So we're trying to find the minimum or the maximum of something. And in this case, when you look at the description of the problem, it says the very last two words say maximize profit. Okay, so that's the objective of this model, is to maximize the profit. So all right, the objective is to maximize the profit, but now we need to write the profit as a formula. Can anybody guess what the formula is? Yeah?
P equals 15x1 plus 20x2.
Why?
Because it's the number of the price and profit of each of the chess set.
That's what it is. Are you sure?
No.
Do you all agree? I'm not saying that it's wrong, I just want you to justify it. Yeah, it's correct, yeah. So each small chess set that we sell gives us £15 of profit. So if we sell x1 of them, we get 15 times x1 pounds altogether. And then each large chess set gives us £20. So if we sell x2 of them, that gives us 20 times x2 pounds altogether. And it's a good habit to, wherever possible, make note of what units these quantities are expressed in. Okay, so in this case, this is the pounds per week that we'll have of profit. So I'll put a note here that this is in pounds per week. It doesn't make the solving of the problem any easier, but it can make the interpretation of what the solution means easier, and it can also make it easier to read what you've written 2 weeks later. Okay, 2 weeks later, you'll come back to your model and you'll try to do something with it. And if you can't remember what you did, then that's not very good. Okay, so we have objective. The objective. Okay, perhaps one last remark. So the objective in these optimization problems. Where's my dot? So the objective is consists of the word maximize or the word minimize as the objective, and then of well, the direction of the optimization, really, you could say, and then it has some function of the decision variables. So in this case, it's just a linear combination of the decision variables. 15 times one plus 20 times the other, and that part is called the objective function. But the objective consists of maximize or minimize and the objective function. Okay, so what are the constraints?
How many hours do you
How many hours we work?
the people working away and the people who are finishing?
Yes. They translate into constraints of the working hours. Okay, so when we look at the workings of the lathes, how many hours on the lathes do we need?
And being large ones less, small ones more. So
Yes.
different associated costs.
Exactly. It depends on how many of each sets we're producing. Now, how many of each sets are we producing? We do. We're producing X1 of the small ones and X2 of the large ones. Well, we don't know the values for X1 and X2, but we can always write a formula that takes X1 and X2 and gives us the number of hours needed on the lathes. Can we not? So what is it going to be, the formula?
3x1 plus 2x2 is less than or equal to 160.
That is brilliant, yes. So 3x1 is the number of hours we need for producing the small pieces, okay? And 2x2 is the number of hours we need for producing the large pieces. And the number of hours that's available is 160 because there are 4 lathes and each of them works for 40 hours a week. And I know the unit here is 160 hours per week. Okay, then the next bullet point. All right. No, maybe before we go to the next bullet point, are there any questions about this, or is that crystal clear to everyone once it's been written? Or is everyone just ignoring it by now?
It's crystal.
Okay. Thank you. Wood. So how much wood do we need?
One for the small, 4 for the large, but we can only have 200 per week.
Does it say 4?
Yeah. The large one is 4 kilograms.
No, so my old slide says 3. There will be trouble. I don't know which one. Yeah, 4. Okay, let's do 4. I think 4 is the right one. There was some old version, draft version from long ago. Okay, so 1 and 4, and we only have 200 kilos per week. So I think Now it's starting to be clear what goes on. And we also have the finisher. And the finisher needs half an hour for each set, no matter whether it's small or large. So how many hours do we need in total? One half of x1 plus one half of x2. And we have at most 31 hours per week. Any more constraints? Yes? How do you know? Yes, that's right. So this is an important part in linear programming. When you're creating your model, it's very often forgotten to add this non-negativity constraint. But it has to be there, because if it's not, well, in this case it has to be there, because you can't make a negative amount of chess sets, even though sometimes maybe you would want to. So in this case you probably wouldn't want to. But I put x1 and x2 have to be both greater than or equal to 0. How much time is left? No, not a lot. Okay, that's it. Any questions about the formulation? No? Good. So now the next step is to learn how to solve this. So how to find the maximum. And we learned 2 methods this year. The first method that finds the maximum is draw a picture. And the second method is called the simplex method. Who's done the simplex method for the A levels in this division? Who's not done it before? Ah, that's good. So it's probably more hands who haven't done it than those of you who have done it. Which is great. Now, draw a picture. Okay, so I don't have the time to draw the picture really now, unfortunately, I think. But so we'll do that. So no, this is the worst thing. You know? It's like I'm saying something, and as soon as I say, okay, we don't have the time for it now, so everybody starts packing. Everyone's left. Yes. So the way it's going to work is we'll draw a planar picture, so a 2-dimensional picture really, in which x1 and x2 will be the 2 coordinate axes, and then we'll try to find the optimal solution like this. But there's no point in starting it now because we should be out in 5 minutes or so. So we'll do that next week. You have Philip this afternoon for 2 hours doing. He will be lecturing on net present values and project assessment. And there is an assignment on that in the lab, so make sure you pay good attention to what he says. And you've got an exercise which is a similar formulational exercise to do at home for next week. Thank you.